Okay, let's go through the exponential decay law. So if let's just say we have a radioactive sample that contains n not number of undecayed nuclei at time equal to 0, right, then the number of undecayed nuclei at a given time can be actually modeled by n equal to n naught e negative lambda t, where n is the number of undecayed nuclei. So n naught, of course, is just the initial number of nuclei. So lambda will be the decay constant and t will be the time taken. Okay, so if you plot against, use your n, right, you plot against t, so this is the exponential decay. So if you look at the time equal to 0, obviously you can see that here is n naught. Then of course, over time, right, the n will decrease, meaning that the number of undecayed nuclei will become lesser and lesser over time. Okay, so based on this diagram, we can actually look at the gradient. So at the start, right, the gradient is rather steep. Then after that, at some time, so let's just say I look at this time. So at this time, right, the gradient is more gentle. And of course, after a long period of time, the gradient is like almost flat, right? Okay, so what does the gradient actually represent? The gradient actually represent your negative dn dt. Because you are you are plotting n against t, right? So the gradient is dn dt. So definitely it's a negative gradient. So it's negative dn dt, which is expressing the activity. So definitely, right, at the start, the activity is the highest. Then after that, you go to here, the activity dn dt, negative dn dt, right, is lower. So means your activity will actually decrease over time, which is consistent because remember, A is equal to lambda n. So A is the activity, lambda is the decay constant, n is the number of undecayed nuclei left. So over time, your number of undecayed nuclei left will be lesser. So definitely your activity will be lesser. So it's actually shown by the three gradient that I draw right here. So the first one, second one, and the third one. Right? Okay, so let's see how do we actually derive the exponential decay law, right, which is the n equal to n naught e negative lambda t. Okay, so first we must start off with a equal to lambda n. So we know that activity is expressing negative dn dt equal to lambda n. So next, you move all the n to the left hand side, all the t to the right hand side. So meaning, so 1 over n dn. Then the negative you put on the right hand side, negative lambda, then dt put on the right hand side. So next you put the integral sign. So integral, right? So meaning that, okay, so for the right hand side, I integrate time from 0 all the way to time equal to t. So left hand side, so at time equal to 0, your n will be the initial number of nuclei, n naught. So after some time, what is left is maybe, let's just say, n. So let's do the integration. So integrate 1 over n with respect to n, right, is expressing ln n. Then put a square bracket. So put n and naught. Later we do the substituting in. So next will be the right hand side, right? So negative lambda t. So of course, we don't need, I mean, we can do the thing. So t 0, right? So it's expressing just t. So it's equal to negative lambda t. Okay, what about the left hand side? Left hand side, ln n, upper limit n, lower limit n naught. So you simply just sub in ln n minus ln n naught. So almost there already. So minus, right? Apply the laws of logarithm. So it's divide. So meaning this part is ln n over n naught is equal to negative lambda t. So of course, get rid of the ln by moving the exponential to the right hand side, right? So n over n naught is equal to e negative lambda t. So move the n naught to the right hand side, n is equal to n naught e negative lambda t. So that is how we actually derive the exponential decay law.